Good morning, afternoon, and evening, dear attendees, and in different time zones around the globe. And welcome everyone to the third IFS seminar. Today's speaker is Edgar Shaghoulian from University of Pennsylvania. Edgar has done his PhD at Stanford by no one else but Susskind, and then has spent some time in beautiful, absolutely wonderful Santa Barbara, and then Cornell, and now he's in University of Pennsylvania. Edgar works in different subjects, including quantum information, quantum field theory, quantum cosmology, and some other subjects which involve the word quantum in them. And he publishes more papers a year than I do in a lifetime. Many of them are in different, sometimes weekly related subjects. Ladies and gentlemen, Edgar Shaghoulian, and he is going to talk today about. Please, Edgar, share your screen for us if you don't mind. It has to do with quantum deformations, but the exact title I read off from its slides in a minute.
That's fine. I don't have a title on the slides, but it says you disabled screen sharing, so I think you need to make me host.
Really? Okay. My apologies. There you go.
No worries. Thank you for the very kind introduction. So this is going to be the first. I just recently got a tablet. Up to now, I've been giving Zoom talks with like slides on my laptop. So this is the first one I'm going to do with the tablet. So I apologize if my tablet skills are not very good, because I promise they won't be. Okay, so sharing, I think, was a success. Okay, so yeah, I spent a lot of time thinking about what to talk about to this group, given that people's interests are pretty broad, and I didn't think it made sense to talk about the kind of latest thing I'd been thinking about, because it was a very particular subject, and it would take a lot to like give enough background for people from different fields to see why I was thinking about the things I was thinking about. So I decided to go back a little bit and discuss some work from a year or two ago, which I guess I should give archive numbers, but I see that Yorit is in the audience, so maybe Yorit, who was a collaborator on this work that I'll be talking about, can maybe put the archive numbers in the chat. So it'll be mostly based on those references, but I'm going to kind of streamline it, because a lot of the stuff we talk about is integrability in the context of ordinary quantum mechanics, in the sense of 0+1 dimensional field theory. And that's a background where everyone, whatever they're studying, that should be a common language for all of us, is just 0+1 dimensional quantum mechanics. And then at the end, if people are curious to ask more about why it is we were looking at these things, please do that. But I will kind of start off mostly with some motivation, and then some formalism, and then a little bit of like various applications. But I won't really talk about the actual applications that we were curious about, just because I'd like this to be potentially useful for other people, because it could have applications that we, of course, haven't thought about. So I will see if I can write with that. Okay, I guess people can see that. So I'll start off with some motivation. The first one is, the real motivation that got us thinking about these things, and it came from some developments in 2D quantum field theory by Zamolodchikov. And I'm not really going to review that. I'll just say quickly what the interesting development was. So he originally studied himself this operator called TT bar, which is a quadratic contraction of the stress tensor in a given quantum field theory. It's a particular quadratic contraction of it. He studied this operator, and then later in a paper with Smirnov, chose to define an RG flow of a quantum field theory with this kind of first order flow that I have here. So S is the action. It can be, let's say, the Euclidean action. Lambda is like a deformation parameter. Gamma here is the determinant of the metric. And TT bar is the quadratic contraction of the stress tensor. So at first order in this deformation, you would deform your theory by adding to it just that quadratic contraction, but then they're higher order terms, okay? And they're all encapsulated by this first order differential flow. Okay, why was this an interesting thing to do? Well, we study RG flows a lot in quantum field theory. Often we start off with a CFT, we turn on some relevant perturbation to the CFT, and then we flow into the infrared. The interesting thing about this quadratic contraction of the stress tensor is that the stress tensor is dimension 2. So this is a dimension 4 operator. In 2D CFT, that means it's an irrelevant operator. So this somehow is going the opposite direction in the renormalization group flow. It starts from the IR and flows into the UV. There's lots of subtleties and things around trying to understand that, but that's why it was exciting, because it seemed that you could potentially understand this flow. And the most exciting thing is that this TT bar operator was universal in 2D CFT. Often to define composite operators, you can only really do that in like weakly coupled theories. You can't just multiply together two operators and produce another one, unless you, again, do it in perturbation theory or have some supersymmetry or some reason that you could define the composite operator. But Zamolodchikov was able to show that in 2D CFT, just using conservation of the stress tensor and cluster decomposition, things like that, that this operator is actually well-defined. It's almost well-defined. It's only OPE singularities are total derivatives. Okay, and it seems to define interesting theories when you start off with the CFT and deform this way. The physics seems to depend strongly on the sign of this deformation parameter lambda. But it seems to be connected to non-local theories. It seems to be connected to gravitational theories. So there's lots of interesting physics there, and that's what originally got us kind of excited and thinking about this question. He also showed, which we'll come to in a moment, the sense in which this is an integrable deformation. You can solve, for example, if you have your initial energy spectrum of your theory, you can solve for the deformed energies. And there's this simple universal formula that he wrote down with Smirnov, and also some other authors similarly wrote down, that you could just compute the deformed energy of the theory. It's given in terms of the initial energy and momentum J naught of your starting theory. So there's this nice kind of universal formula, and then there's other things you could compute as well. And this is true, again, in any 2D CFT that you start with, deformed by this operator. This is the form the deformed energies would take. So there's lots of interesting physics there, which I'm not going to get into. I'm going to sort of quickly move down to 0+1 dimensions, because I don't want to discuss at length these issues of OPE singularities and how well defined the operator is and all that kind of stuff. Okay, motivation 2 is the notion of Wilsonian universality. Okay, this is another renormalization group notion. People talk about it in various ways. I think the simplest way to talk about it is in a sort of QFT 101 sort of way. Let's say we write down, I promise I'd go down to 0+1 dimensions, but that might take a few more minutes. Let's say we write down some free scalar theory in 4 dimensions, okay, with some interaction potential via phi. So one of the first things we're taught to do is to assign dimensions to the operators. So phi has mass dimension 1. So this is the action. Okay, it needs to be dimensionless in units where h bar is dimensionless. That means I have 4 powers of length here. I have an inverse length here and inverse length here. So phi has to have mass dimension 1, inverse length dimension, so that the whole thing is dimensionless. Okay, this is just kind of how you do things in free theories anyway. And what that means is if you write down non-singular potentials, like phi squared, let's say phi cubed, whatever, phi to the n, things like this, these are almost all irrelevant. So remember, in 4 dimensions, a dimension 4 operator would be marginal, dimension higher than 4 would be irrelevant, and dimension less than 4 would be relevant. So, all these phi to the 5th, phi to the 6th, all these are irrelevant. because they're dimension 5, 6, etc. And what that means is the infrared is universal. So what it means to be irrelevant means that if you do some low energy experiment, you're just interested in low energy objects, you can ignore the effects. The effects of all these higher dimension operators can be captured in a very simple way, and you basically don't need to worry about them. Okay, the correlators in the infrared go to some universal things determined by a small number of coefficients, and that is, in a nutshell, the notion of IR universality or Wilsonian universality. Okay, so that is something that features prominently in quantum field theory. But now let's repeat the exercise for quantum mechanics. Okay, I'll change the notation a little bit. So I'll call time tau, and instead of the field variable phi, I'll call it q, just because that tends to be the notation in quantum mechanics. And let's say we write down, again, a similar action. All right. Now, if we count dimensions, the dimension of q is -1/2. Okay, which is very strange. What that means is if I, again, consider non-singular potentials v of q, just like powers, q squared, q cubed, q to the fourth, the interactions in this case are relevant. So quantum mechanics does not seem to have this notion of Wilsonian universality that quantum field theory has. In fact, it has it, but it's sort of flipped. It's sort of flipped, and it seems that the UV is universal. And there's all sorts of stuff that could happen in the infrared, okay, depending on what operators you turn on. So 0 + 1 dimensions is interesting because, again, Wilsonian universality is kind of flipped on its head. And another motivation we had is, how do you modify the UV? Universal, of course, doesn't mean that it's literally always the same. It just means most things don't affect the UV. But we were curious, okay, what things can affect the UV? And of course, you can complain with the type of interaction terms I've restricted myself to here. Maybe you're allowed to put non-singular terms, things like 1/q to the 10th power, or higher kinetic terms, things like that. That's sort of stuff we were curious about. And we also had a lot of quantum gravity motivation, which, again, if people are curious in the end, I can talk about, but I want to mostly talk about quantum mechanics. All right, any questions? That's really all I was going to say in the way of motivation. All right. Okay, you can forget all that motivation now, and I'll explain to you the very simple setting. What are these, what I call the Hamiltonian deformations, or these integrable deformations I'm going to talk about? It's very simple. You take the Hamiltonian of your system and you map it. I'll state it kind of generally at first, and then I'll simplify to the cases we want to talk about, to some function of the Hamiltonian and whatever other conserved charges qi you have in your system. Okay, so for example, let's say we were curious about the hydrogen atom. We could deform the Hamiltonian of the hydrogen atom by some function of these commuting variables. Okay, that's something you can do. And right now, for about half a second, let me just speak generally. I could be doing this in a general d-dimensional QFT, but there's a quick reason why it's a little weird to do that. For d greater than 1, these conserved charges, including the Hamiltonian, which I'm going to take to be conserved charges, are going to be time-independent Hamiltonians that I'm curious about for the purposes of this talk. What we have is that the conserved charges are written as integrals of some current. Okay, so if f of h, if this deformation of the Hamiltonian, or with the q's, is something like, let's say I have something like h plus lambda h squared plus higher stuff, I'm going to come with 2 powers. This is going to imply 2 powers of the integral that defines the charge, and this is a non-local deformation. Okay, so you can consider it, you can try to analyze it, but we were not very excited about this particular prospect because we wanted to start with a local theory and in some sense remain local. That's sort of the hope. But that's why we didn't really think about this in higher dimensions, but it's something you can do. I mean, it breaks Lorentz invariance because you just deform directly the Hamiltonian. It makes your theory non-local. It seems kind of like a mess, so it doesn't seem like there's any obvious application for it, although there might be. All right, so we want to focus on d equals 1. So space-time dimension d equals 1, just ordinary quantum mechanics. And I'll also focus for now, forget about the other conserved charges. If they're there, I'll just imagine a deformation where the Hamiltonian goes to some function of the Hamiltonian. Okay, again, just for simplicity. Now, the first thing to notice is if you have an eigenvector of your Hamiltonian, it's going to remain an eigenvector. Okay, that much is sort of clear. I should probably be putting hats on these h's, but h will always be an operator in my notation. Okay, if I mess up, please stop me. So the first obvious thing is eigenvectors remain eigenvectors. And let me make one more restriction for now, and you can ask, we can discuss the more general case later. Let's say I have a finite dimensional Hilbert space. So I'm really thinking about something like some sort of spin system. This will tell me that no new eigenvectors are created. Okay, this is important. I mean, think about the operator ddx, for example. If I square that guy, ddx squared, that thing will now annihilate a new object, which is x. And so it's important to stay finite dimensional so that we don't create any new eigenvectors. If you're infinite dimensional, generally you can create new eigenvectors, and the eigenvectors won't correspond between the two theories. Okay, so for a finite system, the eigenvectors of the original theory and the f of h deformed theory will be the same. And if you want to think about infinite dimensional system, you can make some more assumptions. And the additional assumptions are basically that nothing weird happens non-perturbatively. You can demand some continuity as the deformation parameter goes to 0, and you land on your original theory, and that'll give you very similar physics. Okay, so I've asked for a finite dimensional Hilbert space. I've done this deformation f of h. I'll also require f of h be strictly monotonic. This is just so I can invert it. Okay, I'll write down a formula in a second that requires f inverse. So I just want f of h to be strictly monotonic. I don't want any energy level crossing or anything like that. So it's some nice smooth monotonic function. I know there are people with math backgrounds, so as far as the, I assume everything I ever talk about is C infinity, even if it's not. Okay, so the eigenvectors remain eigenvectors. That's one crucial thing. And the energy levels are trivially computable. They're these f of e's. Okay, that's just the definition of the deformation immediately gives you the new energy spectrum of the theory.
Edgar, may I interrupt you?
Yeah.
This means that you will deal with some very restricted set of Hamiltonians, because this finite Hilbert space means that conventional Hamiltonians or models of quantum mechanics do not belong.
Yeah, so if I really want it to be finite, then indeed, for example, the harmonic oscillator does not count as a finite system. It has an infinite dimensional Hilbert space. So that already is out.
That, you will deal with some set on compact Keller spaces or something like that. Am I right?
Yeah, I think it'll imply that in situations where that object is relevant. Yeah, I'm not sure though. But I think you can also use this to treat the infinite dimensional case. You just need to make some additional assumptions about how you define your deformed.
You will deal with Landau problem-like systems. Am I right?
Sorry?
With Landau problem-like systems.
Well, for example, this is anything that's finite dimensional, you can consider. So if you want to consider a spin system, that's fine.
But usually these systems assume some compact phase spaces, as far as I understand. When you say, when you consider system on some cotangent bundles of Riemann manifolds, their Hilbert spaces are usually infinite dimensional.
Yeah, I'm being a little bit more lowbrow than that. I'm imagining some Hamiltonian, let's say Ising model like with some fermions, something like this. I don't need to really make any assumptions about this. If these are fermionic with some anti-commutation relation, then this will give me a finite dimensional Hilbert space. So these models I don't need to say anything about. I think these automatically fall under the class of things I'm considering. For ones that are infinite dimensional, again, like the harmonic oscillator, then what you want to do is, imagine there's some deformation parameter. I'll consider this case later in the talk, where there's some deformation parameter lambda. When I take it to 0, I result in the original theory. Then I just want some matching condition of the eigenvectors as lambda goes to 0. So you can define your theory this way. It's a perfectly well-defined theory, but it sort of explicitly prohibits any kind of non-perturbative stuff that could happen as a function as deformation parameter lambda. In particular, explicitly prohibits any new eigenvectors that you might want to consider in your spectrum. So, but for now, I don't want to talk more about those assumptions. So I will be imagining that I always have a finite dimensional system. It can be infinite in the sense of n. If I'll talk about large n systems in a moment, you can take n to infinity. But that, of course, is always a finite dimensional system to begin with. And that's okay. That you can treat that in this class of deformations.
Edgar, can I ask what these functions f of h are allowed to be? So before you told me that maybe it could be a function of h and also L squared or LZ, but now you told me that if you have an eigenfunction of h, it's also an eigenfunction of f of h, but it's not necessarily an eigenfunction of L squared and L of z. So I'm not. So now we're not allowing it to be an eigenfunction of L squared.
No, So that segment was just about the deformed energy spectrum. So if I added additional charges, then I know how to compute the deformed energy spectrum. Whether or not you can compute the deformed charges depends on exactly the algebra that you're interested in. For example, let's say you had additional supersymmetry charges. Let me write down one more equation and then come finish my thought there. So the other thing about these deformations, which is pretty obvious, is that if I have some conserved charges defined in the ordinary quantum mechanical sense, that Q commutes with H, and I have this finite system, then Q commutes with F of H. Sorry, this arrow is going both ways because I assumed F is strictly monotonic, so I could invert it. So I could consider starting with Q commuting with F of H, apply the deformation F inverse, and go to the case on the left. But these two things are the same. So your conserved charges remain conserved charges. And so in the resulting theory, I think what I was asking about is, you have these charges. What about those? I mean, I told you how you can write down the deformed energies. That's one charge. The deformed charges is more case dependent. If you have supersymmetry charges, then there's some algebra you might want that to obey. And then there'll be sort of flow equations. You can write down flow equations for those conserved charges as well, and then try and solve those flow equations for the deformed charges. So it depends on whether or not there's an algebra you want to preserve or not, but there isn't a universal rule the way there is for the Hamiltonian, because the deformation of the theory is defined via the Hamiltonian. So that just for free gives you the deformed energy levels. I don't know if that answered your question, John. But...
Yeah, well, I'm still not sure which. Well, No, I'm not sure if it did. So if your deformation, for example, is h plus L squared, and you have an eigenfunction of h, which isn't an eigenfunction of L squared, then I would have said, well, it's not going to be an eigenfunction of f of h. No, if f of
Oh,
h.
sorry, I was picking commuting charges so they can simultaneously
So if they're
diagonalize.
commuting, right. So what you mean then is that the eigenfunctions can be taken such that an eigenfunction.
Yeah. That's right. Those are the eigenfunctions I'm talking about.
Oh, okay.
Exactly. Yep. Okay. So one final assumption I'll make about the theories I'm considering is just that the ground state energy is zero. Okay, this is a trivial assumption. I can always shift the Hamiltonian by a constant to set it to zero if it's not, but just assume that I've normalized things so that the vacuum energy is zero. Okay. All right. Okay, all right, I said these are integrable deformations. What do I mean by that? Well, I should be able to compute the deformed observables of the theory, right? That's what it would mean for the deformation to be integrable. Okay, and I'm going to write down some formulas that show that that's true. Let's start off with the thermal partition function, which is something you might want to compute in a quantum mechanical theory. So if I want to compute it in the deformed theory, which I'll denote with the subscript f, because f is some f of h Hamiltonian. So this thing is given by some integral. I'm really just writing down the definition of the thermal partition function, but I'm putting in the new energy levels, f of e. Okay, so that's the thing you want to compute. And the first point is that I can take e to f inverse of e to write this in the following way. For some deformed, for some new rho of e called rho f of e, and rho f of e I'm not doing anything fancier than tracking a Jacobian here. The deformed density of states has this simple formula. Okay, so that can be computed pretty easily. You have a deformed density of states. What I wanted to compute was the thermal partition function. Of course, they're closely related objects. So so this is one formula you could write down. This is the deformed density of states in your theory. What does the deformed thermal partition function look like? Well, for that, it's a little easier to define certain kernels. So I'm going to define a kernel which depends on two variables, beta and beta prime, in this way. These contours I'm going to leave ambiguous until I come to specific functions f. Okay, so that's the definition of this object case of f. And what this will imply is that I can transform a Boltzmann factor, some other contour C, okay, so what was the point of defining this kernel? The point of defining this kernel was so I take a Boltzmann factor, let me fix that, that looks horrible. Takes a Boltzmann factor e to the minus beta prime e and transforms it to e to the minus beta f of e by integrating it against this kernel. Okay, so then I can do that level by level on the thermal partition function, which is going to be assumed in a physical theory to be some absolutely convergent object. I can get the deformed thermal partition function by doing this integral. So this is a sense in which the deformed theory doesn't have any new data. There's a simple integral. In cases where the kernel is complicated, you can try and implement it numerically. In the cases I'll talk about, there'll be an analytic expression, and you can do the integrals in certain cases. But this is it. The kernel does the job for you. And the next several observables I'll be talking about will be just repeated application of this basic idea, okay? So that's it. If there's only sort of one thing you remember from this talk at a technical level is that when you deform theories in this way, there are these simple kernels you could define, which once you integrate them against the observables you care about, give you your deformed observables, okay? So let's just write down some examples. So let's say, the examples I'll talk about will be, excuse the notation, it's just the notation we picked. Why is there a 2? Why is there a minus sign? It was just the notation of our paper. And that's how I remember most of the formulas. So I didn't want to change it. So this gives an explicitly computable kernel. Okay, that was wildly optimistic that I would fit this. Let's bring this here. Okay, that's one kernel. And as far as the contours are concerned, so it's important that lambda is less than 0, and the contour is on the semi-infinite real line, so that this thing converges against physical thermal partition functions.
Wait,
Okay,
so can I ask what happens here when you have these other conserved charges? So just the kernel depends on the other conserved charges?
Good. Yeah, so there, what you would want to do, yeah, it depends on what you want to do. If you computed, for example, something of the grand canonical ensemble, sums over E and Q, then you just sort of repeat the trick. So it kind of depends on what happens to the conserved charges, whether they remain unchanged or if they change, if you're trying to preserve some algebra. But if in general you can find, for example, like E goes to F of E and Q goes to some G of Q, then you just kind of want to repeat this, and you'd have two kernels, one integrating against the inverse temperatures and one integrating against the like chemical potentials, so that you transform them independently. All right.
Okay, thanks.
Yeah. Not very efficient at erasing. Okay, and the other deformation, which I'll write down, it's just the inverse of this deformation. It looks a little wild, but it was actually our initial motivation in this problem. And it's the one-dimensional version of what I called the TT bar deformation that Zamolodchikov discussed in 2D. That's why we, again, our initial interest in it came from this. So, and with these normalizations, the reason why there's -2 lambda is because then it's really the inverse of the deformation I've written here. The deformation I've written here is conventional. So then this kernel looks similar. Okay, so these are some, Gaussian sort of kernels with some prefactor. In this case, again, lambda is less than 0, and the contour C is like that of like the inverse Laplace transform. It has a small real part, and then the imaginary part runs from -infinity to infinity. Again, just because these are inverse transforms of one another. Okay, so these are the sort of explicit examples that mostly we studied in these papers. And I'll sort of come to them from time to time for the rest of the talk. All right, that's sort of one way to compute the deformed, let's say, thermal partition function. Another way is like in some sense, expanding the integral and writing some differential transform formula for it, which does a sort of naive thing, which is it takes a Boltzmann factor, it brings down the energy, it manipulates it into the energy minus f of the energy, and then re-exponentiates it. And you can also do that if you wanted. And for some, technical computations, it's actually kind of easier to do this sum than it is to do the integral. But I'm not really going to talk about this this sum version much more. Okay, so that was a simple observable. That was the thermal partition function. I'm going to kind of speed up now because I don't have too much time. So let's say we had a thermal one-point function. Okay, this is defined as a sum over energies E, O, E. How does this transform? This transforms, the energies upstairs transform. And what about these one-point functions? Well, eigenvectors, as I said, remain eigenvectors for the systems I care about, so they don't change. The one-point function of O at any energy eigenstate remains unchanged as long as I'm talking about the same operator O before and after the deformation. And what that means is this thing in the deformed theory relationship to the undeformed theory is the thermal partition function. Again, I just hit it with a kernel. Okay, so no surprises there. So one-point function. Now let's do the vacuum two-point function. Okay, this is again similar. So I'm not doing the thermal case anymore. I'm actually in the vacuum. And now I have two insertions, so I need to give them some time variables. Okay, what do? Well, I evolve the operator O back to the origin. Okay, using that simple representation. And I insert a complete set of energy eigenstates. And what is this equal to? Okay, it again just has sorry, I wanted to do this in Euclidean signature, so I'm going to get rid of these i's. So it has something like that. So again, the formula is the same. If I want the deformed vacuum two-point function, okay, now there's a tau variable instead of a beta variable, but it's the same thing. The kernel now is just a function of tau and tau prime, and the undeformed two-point function sits there. Okay. And you can start deforming certain two-point functions that you care about. The simplest example is to take a conformal two-point function, 1 over tau to the 2 delta, and then you can apply one of the kernels I spoke about before. So if you apply, for example, this kernel, which is for this deformation, the one-dimensional TT bar deformation, this gives you some Bessel function. The answer ends up being proportional with some prefactors to some Bessel function. Okay, so you get some, in various simple cases, you get some nice kind of special function coming out. There's some tau-dependent prefactors and stuff like that. Okay. The last observable, and this really captures everything, I kind of just want to build up to it slowly, is just the thermal endpoint function. Okay, so we did vacuum 2-point functions, we did thermal 1-point functions and 0-point functions, which is just the partition function. So the thermal endpoint function is just a sum over energies. Let's call them E1. And I used translation invariance in time to set one of the operators to 0. And this thing, I can insert complete sets of states everywhere. Everywhere meaning between every pair of operators. And then I have these 1-point overlaps. And remember, the whole key is these 1-point overlaps are not going to change in the deformed theory because the energy eigenvectors are unchanged. And then you have a sum of Boltzmann-like factors. Okay, and these beta i's are just some things that you define. They're differences of the times. This one, this is for like I from 0 to n-2. Tau 0 is beta, and beta n-1 is just tau n-1. Okay, there's some definitions. You would redefine these betas, and these redefinitions are necessary because you have terms that look like this. If you decompose the operators like I did in the 2-point function, you have differences of energies now that enter. So if I applied the kernel directly to tau 1 by defining a k of tau 1 prime, it would take E2 minus E1 to f of E2 minus E1, whereas I want f of E2 minus f of E1. Okay, but that's not like an insurmountable obstacle. You just notice that this tau 1 that hits E2, there's another E2 here that tau 2 hits. So you define the difference of tau 1 and tau 2, and you apply the kernel to that guy, and that transforms E2 to f of E2. And then you do the same thing for E3 and E4 and so on and so forth. And there's enough freedom, if you work through it yourself, there's enough freedom that you can do that. Okay. All right. That's all I was really going to say about the formalism. I'll say in words a quick recap. So the thermal endpoint functions you can write as integral transforms of the original endpoint functions. So in that sense, the deformation is integrable. If you want to connect more to like rigorous notions of integrability, then the closest you can do is the statement about the conserved charges. If your original system is integrable and has some notion of there being enough conserved charges such that you can literally integrate the system, then all those conserved charges remain in the new system. And in some sense, no new degrees of freedom are introduced in the new system. So it should remain integrable. Yeah, any questions about that before I talk a little bit about some applications?
Yeah, hi Edgar.
Hey, Dutarka.
Hey, so does it extend also to S matrices, or means can one define some kernel that relates the scattering cross sections of the original and the deformed theory?
We definitely didn't think about that very much. As you know, in 2D, people have discussed that in defining the scattering matrix for theories deformed by the 2D TT bar deformation. We thought about it a little bit actually in 1D, but I think we didn't go that route because it's not a very natural observable to think about in these. I mean, the systems we're thinking about are things like spin systems and even some classical systems like the Ising model or mean field theory models. And that's not like a very natural observable, so we didn't spend much time thinking about it. But I don't see any reason why you can't. I don't see any reason why you can't define analogous objects.
Always talking means your decomposition is always in energy eigenbasis. That's why these kernels come in naturally. But if they're in some other basis, for S matrix, you will be in X basis or P basis.
Yeah. Yeah, I mean, I think right. I think that adds a technical complication that doesn't make it immediate, but I don't really see.
Yeah,
Yeah,
maybe.
that's an interesting question. Any other questions about this?
Are these form only for monotonic?
Let's see. So in the paper, we oscillated between restricting to monotonic and not restricting to monotonic. For this case, I think, let me see. I don't think you need a monotonic function for these cases. I mean, the monotonic function is often so you can, literally so you could like invert it in cases where you want to invert it. So for example, if you want to write down the formula for the density of states, the simplest way is to invert it. But I don't think you need it for these. Even in cases where it's not monotonic and you want to invert, of course, there's just some zeros you kind of have to deal with separately, and you can write down generalized formulas that work in that case as well. I don't think you need it, strictly speaking, for these formulas. I mean, it's, yeah. But getting the kernels might be a little annoying. You know, okay, there's some formalism, but here, these kernels I'm talking about, we mostly played with them for simple things like this quadratic deformation and its inverse. And then you can sort of compute explicitly and see everything is fine. If you don't have a monotonic F, we don't have any example of a non-monotonic F for which we have an analytic kernel. But I don't think that should be an issue in applying this formalism, at least for these quantities. But don't quote me on that. I've been wrong about whether F has to be monotonic before. Okay. Let's see. I have 10 minutes, so let me think a little bit about what applications I want to talk about. Again, I won't really talk about the application that we were interested in, which has to do with holography. Let me say a few words about world lines. I'll try, well, maybe I can just write some equations since I don't derive them anyway. Yeah, okay. So one interesting thing about this funny square root f of h that I was talking about before is, let's say you applied that to some bosonic system. So I'm going to write, so what's going in these parentheses is the deformed h, and I have n, let's say n bosons. Okay, so this thing is your starting H, it's n bosons, and they have some generic interaction with one another. Here's the deformed Hamiltonian. Okay, I can just Legendre transform to get the deformed Lagrangian. I'm going to leave off the arguments of V. It's Q1 through Qn. Okay, so that's the deformed Lagrangian. Well, why is that interesting? It looks a little crazy. Well, it's interesting because this is a Euclidean Lagrangian. It's interesting because if I can write down, now I'll just write it in terms of the action. I can write the action in a form that maybe will be familiar to people as the action of a world line in a target space. Where there's some non-trivial target space metric. G mu nu is delta mu nu times 1 minus 8 lambda v. Okay, that 1 minus 8 lambda v is just that piece there. And how are these the same? Well, if you take this world line action and work in static gauge, meaning you align the x0 direction with time, and these other ones just have some factors. The square root minus lambda should tell you that this is really only a reasonable world line interpretation when lambda is 0. This shows you that this is world line action for a one-dimensional particle in n+1 dimensional space. If people are familiar at all with the two-dimensional TT bar deformation that I started off with giving the original motivation, there's a very interesting statement, which is if you take n free bosons, the action for n free bosons, which is a CFT in 2 dimensions, and you deform it by TT bar, it gives you some flow between the action for n free bosons and the Nambu-Goto action in an n+2 dimensional target space. Okay, so this is the one-dimensional analog of that. The deformation I considered was the one-dimensional analog of the TT bar deformation. That's this deformation here. And it does a very similar thing. It takes n free bosons. In this case, you can do something more general. You can give them some interactions. In 2D, if you add interactions, it doesn't look like it deforms to Nambu-Goto. But you give them some interactions and you deform it, you can solve for the deformed action, and it's a world line action. Again, for a particle on n+1 dimensional space. Now the potential maps to some non-trivial target space metric. In 2D, the target space metric is just flat. Okay, so there's some connection to world line actions. And notice, since it's a world line action, there are these higher kinetic terms, right? If I take a Hamiltonian, if we think again of something like a harmonic oscillator, some bosonic system, and then I add the square of the Hamiltonian, you should be a little nervous because that's going to add higher kinetic terms, right? And then you have to worry about ghosts. Is this a well-defined system? Is it not? But of course, there's some that we know are well-defined, is when you sum them all up into something like a world line action. And this deformation, while it brings in higher powers of kinetic terms, it does it in this controlled way that sums it up into a world line action, which is something that we can understand. Okay. There's one other connection, which I'll just write a formula for. These world line actions kind of make you start thinking about gravity and whether this theory has some connection to gravity. And we work out in one of these papers carefully that another way to write the deformed thermal partition function, you can write it as a 1D gravitational path integral. Okay, E is the Einbein, which is basically the 1D metric, or its square root. Phi are the original fields of your theory. We're doing a gravitational path integral, so we want to divide by diffeomorphisms. So the initial action S naught couples to an Einbein and has some fields phi. And then there's, in here, there's also some 1D, you can think about it as some quantum gravity action in 1D. I mean, quantum gravity in 1D is pretty simple. But if you do this path integral carefully, gauge fix, control the ghosts, blah, 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 you'll find that you get, this reduces to the kernel formula from before. So there's a way to understand this deformation as kind of like coupling your original theory into some one-dimensional theory of gravity. Or at least there's a formal way to rewrite the calculation. We didn't really go further than the thermal partition function. It's actually hard to show something like this for correlators. But this is intriguing and is connected to, again, something that was seen in the two-dimensional case, which is that the TT bar deformation can be understood as coupling to some 2D theory of gravity. Okay. Any questions about world lines? All right. I'll say a couple other things, a couple other potential applications that we thought about or made some progress on, but not a ton of progress on, just because I think they're interesting things to consider. One will be very quick, so I'll say that now. It's to couple systems. So this will be like the case I was talking about before, where you have more than one conserved charge. So let's say you have two theories defined by Hamiltonians H1 and H2. Okay, if the total Hamiltonian is just the sum of the two if there's no interaction term. But you can imagine adding an interaction term, which is like this, which is just a product of the two Hamiltonians. Okay, H1 and H2 are still conserved charges. So in some sense, there's no like energy transfer between the two. So it feels like they're not really interacting. But what this does is sort of phases the system. So imagine turning this on for finite time. So there's something in, quantum info, quantum info people talk about called the C phase gate, a control phase gate, which is basically this operation on a 2-qubit Hilbert space. So the control means if the first qubit is 0, don't do anything. And then the phase means you phase one of the bits. It's the 1 bit of the second system. So that's sort of the C phase gate. But of course, you could understand the e to the I lambda as like evolving with e to the I lambda H1, H2, T for like a unit of time. And you're in the situation where the Hamiltonians are the same. They're just some qubit Hamiltonians. They have eigenvalues 0 and 1. Okay, so in some sense, you can kind of couple systems in this way to phase them a little bit. And some of the resulting things you'd want to compute should be exactly computable. So that's one interesting thing. We never really found some sort of, killer application for this kind of thing in the original papers. Currently, I'm thinking about it with a graduate student at UPenn, trying to understand in the context of black holes in the thermal field double, if you can sort of phase the thermal field double system in a particular way with these deformations, that will still allow you to compute deformed quantities, because the entanglement structure in thermal systems is related to the interior of black holes. And so we're curious if you could compute exactly some quantities in that context. So that's one thing. And another application is sort of new large N limits. So I'll state this in the context of the SYK model. So large N limits, it's important for your various parameters to scale appropriately with N. So let's talk about SYK for a second. SYK is a disorder average system. So what it means is that these couplings you draw from some distribution. It has 0 mean, and it has some variance, which is normalized in this way. So that's the variance. That's the mean. So in particular, a quantity you want to compute is the disorder averaged partition function. And what that means is you do what's called this disorder integral. So what you do is you compute the partition function for a given draw of the interaction terms Ji, JKL, and then you do an integral over the Ji, JKL at the end, which sounds like an impossibly hard thing to do, but because it's a large N system, you can actually compute various quantities. So for example, there's a large N technique that allows you to compute the 2-point function of the chi's. So this quantity is computable in the infrared. Okay. And SYK, this model was one of our initial motivations again for studying this because it has interesting connections to gravity. But the thing I want to point out is, large N limits are delicate. You want to make sure you have a 't-Hooft-like limit where you, for example, you take N to infinity and take the Yang-Mills coupling G Yang-Mills small, such that the ratio, the product is fixed to scale with N in a certain way, and you can break the large N limit. So if you wanted to deform this theory with one of these deformations, and you wanted to preserve a 't-Hooft-like large N limit, then you would need to scale lambda with N inverse to preserve large N limit. Okay. If you don't do this, then it's a basic point, your action sort of won't scale with N. A simple example is like a Wilson-Fisher theory in 3 dimensions. You can imagine having this deformation. There are some eyes here that are summed over. And it's important if you want to use large N techniques to solve for the infrared theory here, the lambda has to scale with N inverse. And that's just because, you know, large N techniques are just saddle point techniques in the path integral. So you want an overall N in the exponent. And if you don't have your coupling constant scale with appropriate powers of N, you'll mess that up. You won't have an overall N that lets you do saddle point techniques. It's nothing fancier than that. Of course, there's a diagrammatic understanding of what diagrams contribute and whether they're suppressed by 1 over N or whatever. But in the end, you just want your action to have an overall factor of N. That makes it clear that if you deform it, the deformation parameter needs to scale a certain way. And it's a big mystery in the holographic context how to understand these large N limits that are not Toft-like, that don't have this large N diagrammatic expansion. And the context in which they appear are for theories that are dual to M theory in the bulk instead of string theory. So this is like ABJM theories at level k equals 1, or the mysterious 2-0 theory. These things have large N limits that are not Toft-like. There isn't a genus expansion, which makes sense because the bulk is not strings, it's branes. And very little is known about how to compute in these large N systems, any observables. If you have a lot of supersymmetry and stuff, you can compute various things. But this technique gives you another way to do it. These integral transforms I wrote before don't really care about whether how you're scaling lambda with N. So you could, under this deformation, scale lambda as N to the 0. And then there's no, as far as we know or anyone knows, there's no large N technique to compute the deformed correlator. Oops. Can't compute deformed correlator with standard large N. But these integral transforms give you a way to compute these deformed correlators. Okay. So it'd be nice to try and understand this better, to see what sorts of systems you could compute this for. In SYK, we, for example, computed the deformed 2-point function. In the original theory, it has some simple scaling form like tau to the -2 over q. And then you deform it with this deformation, you could compute the deformed 2-point function, some confluent hypergeometric function. It's some mess, but it has a lot of interesting physics in it. So it'd be nice to understand these large N limits a little bit better. And I won't write anymore, but I'll just say, yeah, I'll just end with further thoughts on applications before stopping for questions. So again, with this graduate student at Penn, we've been thinking about various sort of systems that you could apply this to. And we've been thinking a lot more about statistical systems. So okay, maybe I lied and I will write just one thing. So when I talk about H goes to f of H, I mentioned that if you have a bosonic system, then this is kind of a funny thing to do, because if you do something like H plus lambda H squared plus maybe higher powers, you have a kinetic term in the Hamiltonian for a bosonic system. And if you square the Hamiltonian, you'll get higher powers of the kinetic term. We saw this in the world line action. So generally, it's a little bit of a dicey thing to do. You have to be careful and make sure you get a reasonable system in the end. So, and it happens sometimes, like with the world lines. But you're a lot safer if you consider fermionic theories. As you saw in the Hamiltonian of SYK, there's no kinetic term in the Hamiltonian. That's because the kinetic term is linear in derivatives. So when you transform from the Lagrangian to the Hamiltonian, it drops out. So when you square the Hamiltonian or something like that, then you don't get these higher kinetic terms. So it seems a little bit safer. But if you're thinking about spin systems like local systems like the Ising model or the Edwards-Anderson model or one of these, those things are nearest neighbor coupled. And if you square the Hamiltonian there, they'll immediately go from nearest neighbor coupled to everyone coupled to everyone. So it'll make it a lot more like a mean field theory model. So, you know, that you have to be, if you want to maintain nearest neighbor couplings, you can't really do it with this type of deformation. So it sort of seems tailor-made for fermionic models, quantum mechanical fermionic models where everyone's coupled to everyone, because then when you square the Hamiltonian, everyone still remains coupled to everyone. That's what the SYK Hamiltonian was like. Everyone was coupled to everyone. or bosonic models, but classical ones where everyone's coupled to everyone. Classical here just means forget the kinetic term. It's just some statistical model like Ising or Sherrington-Kirkpatrick or one of these. And then you don't have a kinetic term to worry about. And if it's a mean field model, like Sherrington-Kirkpatrick or the p-spin spherical model, then you can square it. And again, everyone's coupled to everyone, so you're fine. You're as non-local as you were to begin with, in some sense. So we've been thinking a lot about those kinds of models and what application they can have there. It's tricky because many of those models break replica symmetry, and then they make the analysis hard. You can't take the existing formulas that exist for the free energy and apply the integral transforms to them because the quenched and annealed averages for these theories don't agree. So you can't just like exponentiate the free energy to get the partition function. But we've still been thinking about application in those contexts. Anyway, I know that was a little quick at the end, but that was mostly for any experts who think about these mean field models. But I hope there's some application to these techniques for things people are curious about, and I'm happy to stick around and chat about any of it. Thanks.
Thank you very much for the beautiful talk, Edgar. Let me remind you that now we have our open questionnaire session, and theoretically it's unlimited time allocated for this activity. So every kinds of questions, of course relevant to the subject, or maybe even not, I don't know. Everyone is welcome. Yeah, please, questions for our speaker.
I'll leave my screen share on for now in case I need to write any equations, but I'm happy to turn it off and make it more of an informal discussion at any point. Wow, no questions.
Well, I have a bunch, but they are irrelevant to the subject, so I'll prefer to wait until everyone else comes up with their relevant questions, and then I'll go.
Maybe I can start. So in the at the end you mentioned that you don't want to have Hamiltonian squared or higher orders that contains kinetic term because you think that the locality structure changes in the theory, or?
Yeah, so I said several things. One of the things was if you just have a bosonic system, again, let's just take the harmonic oscillator, q dot squared plus q squared, something like that. And if I square the Hamiltonian, then I'm having q dot to the fourth term. Okay. Now that's not high.
Hamiltonian does not contain time derivatives, right?
Sorry?
Hamiltonian does not contain time derivatives.
Yeah, no, it's p dot to the, sorry, p to some higher power. It's not quadratic in the moment of p. That's all I mean.
Yeah.
So those systems you just have to be a little bit careful about. For example, if you wanted to write down the Schrodinger equation and solve for wave functions, there'd be higher spatial derivatives in the Schrodinger equation. So you would need like additional boundary conditions or something. It's not a priori a problem. It's just, I think you can pretty easily, if you're not careful, write down sick theories in that way. So that's all I'm saying is that if you're going to apply it to those guys, you need to be careful. The N interacting bosons with, with the particular deformation that I spoke about is an example I like because it shows that you did it in a careful way and got an action that we understand by having studied it in the past is reasonable. And in general, I don't know if you wrote down some crazy deformation f of h and applied it to N interacting bosons, you can get a totally, ridiculous theory. I mean, everything would be computable. So it wouldn't be, like, I don't know what sense it would be sick. You would have a Hamiltonian, you would have energy levels, and, as long as f of h was somewhat reasonable. It's just, yeah, you might be worried about the physical interpretation of such a system. That's the main worry. So that was one statement about the higher kinetic terms. Then the locality I was saying was maybe I'll just write an equation. Let's say I have Ising model which is nearest neighbor spins, right? So you have just some nearest neighbors, and the interactions are amongst nearest neighbors. If you then took this to h plus lambda h squared, so now it's a classical system, meaning there are no kinetic terms or anything. It's just a statistical thing. The path integral is over all configurations. But if I added lambda h squared, now that's going to have a term like this squared. And if I and j are nearest neighbor, but then you square this, sorry, the sum is in here. This is going to couple everyone to everyone all of a sudden. So you'll lose the kind of local structure of the Ising model. There are tons of statistical models that I've studied like this. Again, these are mean field models where everyone's coupled to everyone to begin with. So it's fine. There's not really a problem. It's just if you're interested in a local model to begin with, these deformations won't preserve that. So those were the sort of two worries about these higher powers of H.
Okay, thanks.
Yeah, I mean, SYK in some sense is tailor-made for these deformations because it's, so you can do the quantum problem and there are no kinetic terms because it's fermionic. It's already everyone's coupled to everyone. So when you square the Hamiltonian, it remains that way. And finally, it doesn't break, as far as we know, replica symmetry. And when it doesn't break replica symmetry, you can compute the deformed observables much more easily. You can just take log z, exponentiate it to get z, and then apply the integral transforms to that guy. Whereas if you break replica symmetry, then you have a headache. You have to sort of do things from scratch in a sense.
So then, Edgar, does it mean that if you start from a non-chaotic theory, after deformation, you can land up with a theory that shows this Lyapunov behavior?
No, I don't think that can happen. Yeah, it seems like it would. These things I'm saying sound like if you're kind of locally coupled and then everyone's coupled to everyone, it sounds like things should become pretty chaotic, but it's almost a bit of a fake. In the way that, for example, the interaction term H1, H2 is a bit of a fake. Like they are interacting, but there's no energy transfer. It's just phasing in a particular way. The reason why I think it won't become chaotic, of course, for the Lyapunov exponent, we don't have a good understanding of how it's related to conserved charges of the system. But if we think in the somewhat more basic way of integrability being related to conserved charges and being related to the lack of even quantum chaos, then the conserved charges remain conserved. So in some sense, it should remain either non-chaotic or chaotic. And we computed explicitly for various models. We deformed, like, as you probably know, there's this computation of the Lyapunov exponent from the Schwarzian action. And you can find the maximal Lyapunov exponent. We deformed the Schwarzian action with a pretty general set of deformations and computed the deformed Lyapunov exponent. And we saw that it wasn't affected. Another way, since I know your background, I can give you another example. There's some ADS CFT intuition. If you imagine preserving the large N limit with these types of deformations, then higher powers of the Hamiltonian you could think of as like double or multi-trace deformations. And then you can just think of them as mixed boundary conditions at infinity, the way sometimes people talk about TT bar. And then you sort of see that, for example, if you have maximal Lyapunov exponent, which is controlled by the near horizon physics, it seems unlikely that this would change that. And we also did a concrete calculation in that context and saw that it doesn't change it. So as far as we know, I think we would conjecture that the Lyapunov exponent, if it's maximal, will remain maximal. If it's zero, will remain zero. I mean, maybe if it's just some number, it can change like that. I don't have much intuition for that. But at the extremes, I feel like it should remain at the extremes. But yeah, it's a good question. We spent a lot of time thinking about the chaotic properties.
Maybe one more question. So basically this statement about being able to compute everything in the deformed theory if you know stuff in the undeformed one.
Yeah.
This is not exclusive to Hamiltonian deformations, right? So you could just deform any of the conserved charges.
Yeah, I guess it's a question of what. So what do you mean? Do you mean like a Hamiltonian? So I want to know what the new theory is. So how are you defining the new theory?
I could define, like, if I have another charge Q, I can define now FQ, and in my new theory there will be or you're saying that your theory is given by the Hamiltonian, so once you
Exactly.
I see. But naively, Hamiltonian is one of the conserved charges, and just
Right.
you could be able to transform any of them and define some new theory in some way, but maybe.
Yeah, no, I'm right. I'm not sure. I mean, of course, you know, if you start with a Hamilton, let's say you don't change the Hamiltonian as you're suggesting, and you want to change one of the Q's, it's like the same argument as before. If Q commutes with H, then F of Q is going to commute with H. That's just some other crazy charge you could have defined. It's of course kind of redundant with Q itself, so we don't really think about it. And I wouldn't really know how to define kind of deformed theory in that way. Again, unless it like entered in some non-trivial algebra, like the supercharges that I referred to before. I mean, those things have to anti-commute to the Hamiltonian. So if you flow the Hamiltonian, you're going to flow those guys. So you can think about it the other way around. Say, maybe for some reason it'll be natural to define a flow of the supercharges that you care about, and then see what that has to induce in the Hamiltonian. So in those cases, I think you're right. You can define the flow theory that way, and the same sort of ideas will be true. But like very generally, if there's no non-trivial algebra, I think you wouldn't really have a deformed theory in any sense. But I guess maybe one thing, yeah, okay, if you a pure mathematical statement you can make, I guess, like what you're saying is, if you deform the charges Q to F of Q without deforming the Hamiltonian, you can imagine computing some object, which is like the grand canonical partition function, which is e to the sum over e to the minus beta e plus mu F of Q. It's just some new object you want to compute. And you can compute that object with like these kernels. I guess that's something you can do. Yeah, not obvious what the physical interpretation is, but it's something you can compute, I guess.
Would it be possible to modify your theory to cases where FH doesn't commute with H? For example, when instead of lambda you have, well, where lambda is not a number but an operator, and for example you have H plus an anti-commutator of lambda and H square, you know, like something like this.
Yeah, I wouldn't know how to do that. I mean, there's probably cases you can do where, let's say H doesn't commute with F of H, but if you like commute it finite number of times, you eventually like hit 0 or something. Like probably that generalization you can do. But if you just stuck in a general operator in your theory there and had no commutativity, I don't know how you do it because of these. I didn't focus on this, but there are these OPE coefficients in all the formulas, which, if I go back to the beginning, were pretty important. These guys, and these things not changing. That it was pretty important that the deformed Hamiltonian was F of H. Otherwise, the deformed formulas, you'd have to track the change in these eigenvectors as well. Like in the 2D analog of this story, Yorit, who's in the audience, has thought about this question. And then it's a lot harder because these eigenvectors flow, and then the formulas are kind of a mess. So you get really lucky by picking this very special kind of deformation.
I see where the source of complication is. Yeah, thanks.
Yeah.
I'm trying to understand what values of lambda I'm supposed to use. So is the logic that I should take lambda infinitesimal and then I do the flow away from the UV fixed point and I get to where I get, or am I allowed and maybe get some other operators, or does it live in some sort of bounded set, or what lambdas can I use? I mean, in some cases I saw the square root with which becomes negative if lambda is too big. So that one, I guess it's bounded. But...
Very good. Very good. Yeah. So there's, oops. So there's this formula that you were talking, right. So to answer your question, you're of course under, to say something we can all agree about, you're of course under most control if you treat lambda perturbatively. Then you could even compute using perturbation theory and then be fine. And in the 2D version of TT bar, that's really where things are well understood. And then there are complications that happen at finite lambda. Many of those complications are related to exactly what you just said, which is for the most part, people have focused on lambda as positive in the notation I've chosen here, where there is this zero that you're talking about, where the energy levels would complexify. Now that has a very interesting interpretation in ADS CFT, but of course it's weird. Your energies are becoming complex. You have to understand that somehow, and it's still not totally understood what this means. One thing you can kind of quote unquote do in the quantum mechanics case is to declare that your deformed theory is these energy levels where you truncate the energy spectrum above where they become complex. Okay, that's in principle well-defined, but practically impractical. It's well-defined, but impractical way to talk about your theory. You won't really be able to compute very much for interesting theories. So to come to your point, indeed, if you have a deformation like this and lambda is positive, you can run into trouble. And it's not really clear how to think about the resulting theory. You can still compute everything formally and it's fine. Really the case that makes more sense is lambda negative. And in some of these formulas, like when I wrote down these kernels and things, I sort of quickly snuck in that I want lambda to be negative, so that these transforms and stuff were well defined. And often to get to the lambda greater than zero case that we often cared about for holography reasons, we would analytically continue the resulting formulas. But that final step is a bit formal, and the physics of it is not well understood.
Okay. So in the beginning of the talk, you were telling us about these flows into the UV, going away from some sort of a fixed, well, going away from the UV fixed point, and so these keep the same sign as lambda. So you'd start with an infinitesimal lambda, which is positive or negative, and it would grow bigger and bigger until something happens. Is that how it works, or and maybe get some other operators, or how does lambda go together with its flow picture?
Yeah, you can think about it either. Let's say we had this one, h minus 2 lambda h squared. You can either just imagine sort of cranking up lambda, and that's like it. You're just choosing a particular trajectory in your theory space by doing that. Or you could think about adding kind of higher and higher terms. Because this case is some controlled quantum mechanical case where the OP structure is what it is, you're sort of fine thinking about the theory just like this without having to add additional powers of the Hamiltonian. And that just defines a particular direction in field theory space. And it's sort of, in the 1D case, it's sort of up to your design to flow through theory space however you wish. You can add, some other lambda tilde, h cubed, lambda tilde tilde, h to the fourth, and just choose your trajectory as you wish. But then as they say, there be dragons or whatever.
Yeah, I mean, so in the Wilson case, I mean, I kind of understand what I'm doing.
Sorry, I think you cut out for a second. You said you understand what you're doing, and then I didn't hear the rest. Can anyone else hear Jara?
I think we have lost connection with him for a moment. Let's wait for a couple of seconds if you don't mind.
Okay. No, that's fine. In the meantime, I might see if I could plug in my laptop.
I lost the internet, but I was trying to ask, so in the case of the normal flow going down to the IR, I mean, I understand how what you're doing is well defined. So you're integrating out very fast to short wavelength degrees of freedom. And so what you get is clear. So here you were mentioning doing this flow backwards. So what exactly is the prescription? I mean, how does it work? Flowing into the UV. And so how would I even ask the question? I mean, about what happens to lambda as I'm flowing into the UV?
Well, so in the 1D case, lambda is just the parameter you design. You can choose it to be what you want it to be, and that chooses just another point in the field theory space.
Right. So lambda I can always choose, but in the beginning of the talk, but maybe it was just supposed to be motivation. I mean, you were talking about how it's natural to do Wilson's argument backwards about flowing into the IR, that now we should think about flowing into the UV away from this
I think
towards the UV fixed point.
Yeah, I mean, in the quantum mechanical case, I think if I don't think about, so in the 2D case where people are excited about this, I think it's a lot less well understood. I think in the quantum mechanical case, you can kind of think about it almost in an inverse of the inverse way, which lands you on the same picture, which is think about the f of h theory. It is what it is. It has some additional UV degrees of freedom that you've introduced, like higher kinetic terms or different potentials or whatever. And then you flow from that into the IR and land on your original theory H. So in that sense, you can sort of, you can start from this guy or whatever, whichever one you want, start from f of h and imagine doing Wilson and ending up with H. And I would think about it as just the inverse of that. As you say, it's not.
It's not invertible, no? I mean.
Which?
Well, the flow into the IR isn't invertible. You can't get back to a unique flow to the UV just by demanding that it have that right inverse.
You're right. That's the usual intuition. I mean, in the 2D case, because this TT bar operator is special, it's believed, again, it's not totally rigorously understood, it's believed that the flow it defines, if you start from a CFT and deformed by this operator, is a unique flow. So if you choose to vary that parameter lambda, then that defines a trajectory in your field theory space, and it's believed that that coincides with the RG flow. And in like perturbation theory and stuff, people have computed various things. Here, powers, so I didn't really say this, but powers of H are manifestly well-defined. They're conserved charges. These are the composite operators, which are trivial to make well-defined to begin with. So the thing that leads to this ambiguity, I think, in the inverse type of RG flow is that these irrelevant operators have all these short distance singularities. And then when you want to regulate that, you have to choose a prescription. And that prescription is not universal. Depending on the theory you pick or whatever, there can be lots of things you can do. And there's no sort of unique upflow into the UV. In this case, because H squared and stuff is totally well-defined, the UV theory is well-defined. I mean, it's just this thing. We computed the energy levels, all the correlators. That was the theory you had. And this is, by definition, where it lives in theory space.
Right. Well, so the problem isn't that flowing into the IR doesn't have an inverse. It's that it doesn't have a unique inverse. I mean, that's what it means to not be invertible. So this is an inverse. But the claim is that there would be other theories which are also inverses. So different kinds of UV theories which could flow to the same thing when you're going to the IR. Right? That's what normally happens with Wilsonian flow.
Yeah, I think these flows, though, what's believed, and I think it's just true in the 1D quantum mechanical case, is that they're uniquely invertible.
Oh, okay. So
and that's tied up into the fact that the deformation is like a totally well-defined composite operator. So in the case of TT bar, that thing was almost well-defined. And then these higher powers of these conserved charges are just very well-defined. So there's no ambiguity coming from these singularities that you have to worry about.
Okay, so if I tried to cook up another UV theory, you're saying I'd run into trouble making it well-defined. That's the claim, I guess.
If you tried to cook up another UV theory.
Yeah, if I tried to deform lambda a little bit and then say, well, what's going to happen?
That flow to the same IR theory, you mean?
Yeah. Right, that's what it would mean to not have a unique
Yeah.
inverse, that there's something else in the UV. Because normally I think, well, in the same universality class, you've got all kinds of stuff in the UV. So it's kind of strange hearing that there should be something unique in the UV.
Yeah, exactly. That's one of the reasons why people got pretty excited about this. For example, again, this is like classical computation. That's why I say it's not totally understood in the 2D case, but these sort of deformations of the actions I was talking about, like if we started with the end-free bosons or whatever, classically it's just true that if you deform that thing, it leads to the Nambu-Goto action. And I forget what the latest is, and people trying to understand this flow actually like quantum mechanically. But I think I think, right. I think let me think about this for a second. Yeah, I think it's important to know how you approach. So if you imagine you start with theory, you flow to the UV, and now you imagine reversing it. I think it's important how you flow into the IR theory, because of course I'm talking about deformations of general theories, harmonic oscillator, higher dimensional free bosons, or whatever. Those things clearly, as you say, since they're universal, you can flow down to them from other UV junk. But I think the sort of leading operators that exist as you approach the fixed point are important. And this flow is a particular flow that has a particular set of leading operators. And that's the thing that sort of gives it some uniqueness. In some sense,
unique given those leading operators, you're saying?
Yeah.
That's the uniqueness. Oh, okay. Yeah, sure. Okay, thanks.
Mm-hmm.
Further questions for Edgar?
I'll stop the share, make it more colloquial.
So if there are no urgent questions, then maybe I dare to ask a couple of questions regarding irrelevant technicalities, if you don't mind.
Yeah, sorry, I missed your message about stopping for questions.
That's fine. You still did stop a couple of times, and that was
Great.
That was satisfactory. So one thing I wanted to ask about is, well, I first would like to come back to the comment made by Dr. Nersisyan regarding the compactness. Well, if you consider, say, an infinite dimensional, well, in finite dimensionals, everything is fine. So there are no technicalities. I have nothing to ask about. So let's try to go to infinite dimensions. So if your operator H is compact, then you have discrete spectrum. And if you have discrete spectrum, you have eigenvectors in the proper sense, right? And then everything in principle should work as in the finite dimensional case.
In the proper sense, you mean that they're normalizable as opposed to just delta function normalizable? That's what you mean?
I mean, or even to put it even better, they are eigenvectors in the sense that they belong to the Hilbert space.
Yeah, yes.
Right. So in that case, the machinery in principle works as expected. And that's why Dr. Nersisyan was suggesting that you consider maybe systems, quantizations of classical systems on compact manifolds or cotangent bundles of compact manifolds, because if the manifold is compact, then the operator is compact, and then you have discrete spectrum and things work as expected. But then when you go to non-discrete spectra, so I want to ask what are your assumptions about your quantum mechanical system and about the function f, so that you make all that really work out the way you suggest. Because the most general quantum mechanical system is simply a separable complex Hilbert space and a densely defined self-adjoint operator and nothing else. So in this context, if the spectrum is not discrete, what do we mean by an eigenvector? So, how do you define f of h as another densely defined self-adjoint operator for which functions f?
Yeah, sorry.
Yeah.
Right. My entirely unsatisfactory answer to that question is I always think, even in the context of quantum field theory, where things are, even more infinite, as having an IR and a UV cutoff and a discrete spectrum. So I don't know. Let's see how this is. Yeah, I don't know any. I would say I don't know any case. No, that's not true. Okay, most cases I think about, again, we can start even more generally with quantum field theory as really sort of lattice regulating in a way where your lattice action is really such that your energy levels are discrete. And then I just think about that theory. Of course, well, the whole industry of trying to then take a continuum limit to land on the theory you cared about in the first place. But because the subtleties you're pointing out are important in trying to deal with it directly in infinite dimensions, we didn't really do anything for that case. When I was talking about infinite dimensional stuff, I was really thinking about the discrete case where the operator still makes sense, everything is ordinary, normalizable, and then you just make a restriction that no new eigenvectors are created by some smoothness condition as the deformation parameter goes to 0. In that case, I know what I'm talking about. In the continuous case, yeah, I only think about it as, again, like a lattice type theory.
Good. So now let's go to that case then. Suppose that you have a compact operator which has a discrete spectrum, and then it has proper eigenvectors and which comprise a complete set, which is a spectral resolution of identity. Now you have a function f. So first question is, what's the class of functions f that you admit?
So I guess in the paper, we're mostly thinking about, strictly monotonic, infinitely differentiable f. I mean, our attitude was whatever property you would want it to have, assume it has it. But I think insofar as we thought about it, I think strictly monotonic, infinitely differentiable was sufficient for the formulas that I wrote down.
Right. Then if you have f c infinity, then there are basically two different ways of thinking of f of h as far as I know. And the first one is thinking of it as a spectral multiplier, in which case it acts in the spectral representation of the original self-adjoint operator by multiplying the function instead of lambda by f of lambda. So the spectral multiplier. And in that case, the original spectral resolution for the operator h still works for f of h. So I don't see how you can have a situation of f of h where the original spectral resolution doesn't resolve f of h. Of course, you may get new eigenvectors in the sense that originally different eigenvalues may become the same after taking f of h is f of is not injective, in which case you get eigenvectors which are linear combinations of formerly different eigenvalues, so to speak. But that's not a problem because the original system still diagonalizes the new one. And the
Sorry, if you choose that it's strictly monotonic, that what you said can't happen, right?
Yeah, that's exactly what I'm saying. So if you take a monotonic or more generally an injective function f, then I don't see how, in which way or in which sense there can happen a situation where the original resolution of identity doesn't diagonalize the new f of h. In which sense do you define f of h so that such a situation can occur?
I mean, we were trying to explicitly rule out that case, so we were generous with our assumptions. And maybe what you're saying is correct, that you can't ever have that happen. I was just worried about, again, in terms of like writing down. Yeah, I guess the case I was right. The naive case I had in mind was not in this discrete case. It was kind of in the continuous case. So it was a continuously infinite case. This is just DDX operator that I was talking about. If you square it, now it annihilates X. So it has this additional zero mode. But I guess what you're saying is if you are actually discrete, then you can't ever have something like that happen. Maybe that's true, or I guess you're telling me that's true.
Yeah, I believe. I mean, the way I am taught as a mathematical physicist, the way I know you can compose f of h, all those ways lead to a situation where the original eigenfunction still work, and so the original spectral resolution still works. Now, even if if you are in the
the original eigenfunctions work, but there's the question of whether there's a new one that's created that you're missing, right? That's the worry.
Yeah, the worry is whether or not the original spectral resolution diagonalizes the new operator, and that is the case.
Why is that's what that I guess you're just telling me is true, right? I don't see why it has to be
that's
true.
True if we are following those ways of defining f of h which I know of. So if you have come up with a new way of defining a function of an operator which I'm not aware of, then that might be well the case, that you produce something that is out of control. But those standard ways of functional calculus that I know of, they never produce such a thing.
That's great. I'm happy to hear it.
Yeah, and also for the continuous spectrum case, you're right. So for d by dx, if you square it, you get d squared dx squared, which annihilates x. But still, you have no problems with that. You know why? Because x, being a generalized, in Gelfand sense, eigenvector for d by dx squared, still is not a member of the spectral resolution. So you still have the same situation. The original spectral resolution still works. So you do produce new eigenvectors, but these eigenvectors don't matter for the spectral theory because they can't be approximated by a Weyl sequence. So they don't really play a role in spectral theory.
Yeah, you're saying for these formulas where I had these OPE overlaps and stuff like that, I'm still fine with the set of E's that I had from before. Yeah, I was worried, I think, in a generalized sense of being able to tell someone when they hand me the deformed thing, like, here's your spectrum, here its eigenvalues. I guess I'd be missing some of those. But yeah, I think I understand what you're saying, that still these formulas would follow because you can still resolve the identity.
Exactly. And that's because, I mean, these bad eigenvectors, they don't participate in spectral theory. And the spectral theory is what you care about, because the spectral theory exhausts the Hilbert space. The Hilbert space is your physical space.
Right.
May I ask, may I interrupt you, Gerard?
Of course, please.
Edgar, how important was your requirement that your spectrum is finite? So
well, I guess that's what we were just talking about. I mean, yeah, I guess that's what we were just discussing. I mean, I declared it to be finite and implicitly also discrete, just so I wouldn't have to worry about any of these subtleties. As Gerard said, he has no question in that case. That's why we were kind of making it that as a strong assumption. And Gerard, I think just pointing out all the ways that you can imagine weakening it and still keeping some of the results. So he tells me that for these integral transform formulas, for example, they seem to be fine even if you have it being continuously infinite dimensional, because your spectral representations are still preserved.
Should am I right that actually all these things could be more or less directly extended to discrete but infinite dimensional spectrum?
Yeah, I think if you wanted to compute these deformed correlators, I mean, I'd have to think about it offline myself. It sounds reasonable. The thing that I was mostly worried about, again, because there are these holographic applications where I sort of really cared in some sense about the deformed spectrum, even if they were like things that weren't officially in the Hilbert space, like these delta function normalizable things. I was still curious about those, so I was nervous about that case. But I think it sounds reasonable that these formulas don't care about that, and they should still work.
Well, understand. Okay, thanks.
Mm-hmm.
And one more question, if you don't mind.
No, I don't.
It's been a while, so you may be exhausted, but let's try to go as far as it goes. So you talked about the locality in the sense of an Ising model where objects are interacting with only nearest neighbors and so on, but there is another kind of very basic, much more basic sort of locality that has to do with the operator at hand. So when you take an arbitrary function of the original operator, say if your original operator h is a differential operator, then it's local in all possible senses that ever can appear in physics. But when you, for instance, take f of h and
wait, sorry. Wait, any differential operator? Like, sorry, do you count a sum of d dx to the n over all n? Does that count as a differential operator?
No, it doesn't.
Okay.
A differential operator has a finite order by definition.
Okay.
Right.
But that thing, I think I guess the spin people would call something like that k local. But yeah, I'm with you in spirit that it's basically local. Yeah.
Yeah, there are subtleties there. And the question is, even if you take something as benign as square root of 1 plus h squared, for instance, I'm saying this is benign because, well, its growth at infinity is polynomial, which means that it preserves the convex hull of the support of your wave function when you act upon it. But it's still not local in the following sense. So if you have, say, a wave function which is localized somewhere here and then here, so two dense sort of bumps in your wave function, everywhere else it's zero. If you act on such a wave function by a Hamiltonian or an operator, an observable f of h, which is something like 1 plus d squared dx squared, then it suddenly becomes non-zero all the way between 1 and 2. You see, it's sort of a little bit spooky on this very basic locality level. And there is actually necessary and sufficient condition for the functions f for which this doesn't happen, but that's an sort of work in progress. So
sorry, I'm not sure I quite understood. I have some wave function psi. I can represent it as in a basis as psi of x. That wave function psi, if I act on it with f of h, will remain unchanged by definition. That should
I'm
remain.
saying that if your original wave function psi of x, say if you take its absolute value squared, the corresponding probability distribution, okay, in a sense.
Yeah.
Then it's supported only on two tiny intervals, certain distance apart, right? A little bump here and a little bump here.
Yeah. Is this psi an eigenvector, or do you not care?
It doesn't matter. It doesn't matter.
Okay.
The point is that if you act upon it by a conventional Hamiltonian, like a differential operator, the differential operator are support reducing. So what you get as a result is still within these small intervals, maybe even smaller, right? And that gives you some kind of locality in the sense that there is no sudden action on distance. But when you act upon such a wave function by an operator like square root of 1 plus h squared, where h is a differential operator, but the new one, f of h, is not a differential operator anymore, right? What you get, your resulting wave function is smeared all along the way from 1 to 2. It's not localized that way anymore.
I see. But for you, it was important that the resulting operator had the whole infinite series of DDXs. That's the
it doesn't matter. This is unrelated to the first question. So it is just saying that when you take non-polynomial or non-certain property functions f of your original differential operator, you may end up with Hamiltonians which lose that kind of very basic locality. And
yeah, right. I was just checking that the feature you're putting, the non-polynomial thing in this example, is just because square root 1 plus h, if I expanded it out, it would have all the powers, and that's the important feature.
Right. So it's and most importantly, it's not an entire holomorphic function, right? And that spoils it.
Right.
Yeah, but that doesn't have to be relevant to the subject in question, just a comment. But one thing I wanted to ask really as an interpretation is this. Again, a third unrelated thing, if you allow me. Classically, on say, a Poisson manifold, when you take a smooth function of the Hamiltonian, what you get as a result, as a new system, is basically a reparameterization of time. Because if you plug f of h in Poisson brackets, you just get an overall factor f dot out of the Poisson brackets. Right? You can incorporate this into a new time parameter. But in quantum mechanics, of course, you don't have just one energy level. For each energy level, those time reparameterizations would be different. But could you maybe give some kind of analog of this, or whether it makes sense to think of it in this way?
Yeah, that's an excellent question. Right. So when we wrote down these deformations, there's of course a feeling anyone should have when they're first faced with an f of h deformation of, well, this clearly looks kind of stupid. Is this doing anything interesting, or can this just be repackaged? And we've thought about this a little bit. And in the formulas, it doesn't seem like in the quantum mechanical formulas there's anything as simple as something like taking time to f of time or f inverse time. There wasn't some simple reparameterization of time. So we thought about in that case, and that didn't really seem to work. For some quantities, it was relevant. Like if you did the h plus lambda h squared deformation, and you thought about a conformal correlator that went as 1 over tau to the 2 delta, and then you deformed it and then went into the UV, it would effectively cut in half the conformal dimension of the operator. So in that sense, it was doing something that felt like just kind of like a simple rescaling, but the full function itself didn't seem to have any nice interpretation like this. Now, in the classical setup, sorry, maybe you can repeat what you're saying, that an f of h deformation in the classical setup is captured by, what's the exact reparameterization of time?
Well, if you denote by s the integral from 0 to t of f dot qt pt dt, then you can show that the new trajectories follow x of s instead of x of t. Because if you write down the Hamilton's equations in the way d by dt of f equals Poisson brackets of f and h, if you plug some capital F of h instead of h, you just get an overall factor because it's first order differential operator, right? It just pops out as an overall factor. So what you get is simply a reparameterization of time along each trajectory. But yeah, I'm not sure whether this gives anything meaningful in quantum case. So that's why I'm asking if you have come up with anything like an interpretation like.
No, we wanted to, and we were curious because we were nervous the entire time that this is some trivial thing, and even in the 2D TT bar type deformation, and even in this one, for certain types of f of h's, it seems like you could repackage the deformation in the 2D case as like a change in your background metric, which is effectively like saying a reparameterization of space-time. That was only true for particular f of h's in the 2D case. In the 1D case, seems a little bit more general, like a bigger class of f of h's could be understood this way. But there didn't seem to be any totally general thing. I feel, well, you tell me, but I feel like it must exist in the math literature that if you do this, this is just repackaged in this simple way, and it's really like your original system again. But I guess since you're asking me the question, it's not an obvious thing in the math literature.
It's not, as far as I'm aware, it's not.
Okay. But I'm curious, yeah, about the classical case. But I wonder if the statement you made was something about classical trajectories. Is there? I'm wondering if there's any relevant similar statement for these like spin systems I was curious about, which are classical in the sense that they're just statistical path integrals. But there isn't, as far as I can tell, an obvious way for some of these models of writing down the deformed quantities in terms of the original quantities if I deform the Hamiltonian. I mean, there's no time. So I don't see how it would work in that case.
Okay, I just asked some related question, Edgar.
Yeah, please.
Since you deal with this system with finite dimensional space and so on, did you try to? It should be natural formulation in terms of this localization formula. Did you try to do this?
No. I'm not sure what you mean, but I'm pretty sure we didn't try to do it.
I guess it's related with your question to yourself that these things should be. It seems that they should be naturally formulated in terms of this formula. Now, okay, in its initial sense, in its initial formulation.
Yeah, I don't see how, maybe you can say more. I don't really see how you'd reformulate it as like a localization problem.
Well, you deal with some finite dimensional Hilbert space.
Yeah.
And this means that you formulate your system in some compact phase space. Okay. It's just some intuitively that all these things could be reformulated or formulated in localization, via localization, in around classical trajectories with some respective weights.
Yeah, maybe. I wouldn't know how to do that, but I guess, well, the classical problem, I guess Jair is saying that you can
reformulate all these things. My question, you understand? It's not some intuitive question.
Yeah, no, we did not reformulate it that way. I don't even know enough to know if that would be easy, hard, trivial, very hard. Like I haven't thought about it at all, and it'd be interesting to think about. I mean, yeah, because the stuff is kind of integrable and has these simple answers, I'm sure there are more standard ways to think about it. I guess in the classical case, when you're curious about trajectories and times, you're saying there's a totally standard way to think about it. I think in the quantum mechanical case, there must be, again, some simple way to think about it, which we hadn't understood. Maybe localization techniques in the quantum mechanical case are one way. I don't have anything useful to say, unfortunately.
Any further questions for Edgar, please?
Enough questions.
So if we don't have urgent questions for the formal part, then let's conclude the formal part